by knowing the electron configuration, we can look at some different properties about some elements. We can see whether something is diamagnetic or paramagnetic, whether it opposes a magnetic field or produces a magnetic field. And then we can also tell something about colored solutions or non-colored solutions. You guys have done enough in lab now to know whether or not you've had a lot of solutions and pipettes and stuff. What did you notice about most of the solutions that you've worked with? What do they all look like? Most of them. Most of them, what color are they? You're saying white. Are they really white or are they clear? They look just like water. A lot of them do. So we have a lot of solutions that we work with that are clear, but there are going to be some that are colored as well. So the way we can figure out by looking at electron configuration whether or not something is going to make a colored solution is whether or not it has unpaired d electrons. So it's key to think about the d electrons, just not unpaired or paired. And this will help us to predict whether or not it's a colored solution. So our first example, we've got our potassium ion. If we wanted, and this, maybe on this first one I'll do orbital spin diagrams, but then after that I'm just going to draw the electron configuration. So for potassium, the ion where it's a +1, everybody sees that that's number 19. Who would that be isoelectronic with? Argon. So it's going to be, I'm just going to go ahead and say neon, and then the 3s2, 3p6 is what potassium ion looks like. So if we were to think about our spin diagrams, you would have your 1 orbital here for your 3s, and you've got 3 for your 3p. So when you look at your arrows, it's up, down, up, 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 down, down, and down. So the question is, do you have any unpaired d electrons? No, you don't even have any at all. So there's no d electrons to even worry about. So in this case, we would expect this to be a clear solution because there are no unpaired d electrons. Okay, then we get to Ga+1, gallium. For this, we're going to say that it's argon is our most recent noble gas. And then after argon, it goes to 4s2. So gallium is number 31. So it goes to 4s2. And then what? Not 11, can't be 11. 10. And then if it were just gallium, it would be 4p1. So now we think about what happens when it gets that +3. What does it do as far as electrons go? Loses those 3 electrons. You're looking at this thinking, yep, I know where to take those from. You take them off, and that is what the electron configuration is like. I could draw spin diagrams, but you can look at this and know that what? Do we have any unpaired d electrons? No, they're all paired up. Yes, we've got d electrons, but they are all paired up. So we don't have to worry about any unpaired d electrons, meaning that gallium, when it forms a solution, it will form a clear solution. You know, another thing, let me just kind of back up for a second and just point this out, that if something forms a solution, that means we took this solid, we threw it into water, we stirred it up, and it broke apart into ions. So that's why we're seeing all of these listed here as ions, is because it is in solution, so it breaks into ions. So you always have to think about it as an ion when we're talking about it in solution. Okay, next one, we have cobalt +2 ions. And here we would have argon as our most recent noble gas. And then what? 4s2, 3d, 3d7. Okay, so there is our electron configuration for the neutral atom of cobalt. It's not neutral, it's got a +2, so it's going to lose 2 electrons, and those come from where? The 4s. Those go away. So what we end up seeing If you need to, you can draw some orbital spin diagrams. You could draw some boxes on those, but you could look at that and are there any unpaired electrons? Yes, there are. So would it be colored or clear? Colored. And then finally, the last one is going to be zinc. Again, this is going to be argon. And then we're looking at number 30. So this is going to be 4s2, 3d what? 10. So when it loses those two electrons, see ya. Do you have any unpaired d electrons? Nope, not so much. So it's just going to be a clear solution. So that's what we have as far as metal ions go. Okay, so now we're getting to Lewis dot diagrams. And what this does is this is a way of representing those valence electrons. And if you need to at some point, you can refer back to your periodic table that we looked at yesterday, where we wrote the valence electrons across the top. But we're going to show the electrons that have that highest principal quantum number, that highest energy level. And we are going to represent those electrons with dots that are placed around that element symbol. So maybe somewhere you can just draw something like this, that you're going to have your element symbol. And then if you think back to what we've done a couple different times, we've talked about these orbitals and sublevels. So we've also seen that the valence electrons only come from your main group elements, which are right over there. Remember where those are on the periodic table. You've got your S and your P. That's your main group or representative group. They'll never come from the D block or the F block. So when we do our dots, and you're going to think about having a box around that element, but you can fit 2 electrons into this area. Those are considered the S. Those would get filled up first before then coming back and fitting up to 6 more electrons into your P block. So that's what this is going to look like. If you just want to have that little symbol, first of all, just to kind of show what those Lewis dots are going to be doing. We're interested with these because these are the ones involved with bonding. So now, on my board here, I have plenty of room to be able to do dots right around the actual symbol that I have, but you guys might want to rewrite. For example, you might want to rewrite lithium just so you have space and maybe move them around. And we're going to go ahead and show the dots that represent those electrons, and those are called Lewis dots. So, looking at your periodic table, you could do the electron configuration for this, but you now know the shortcut. Looking at your periodic table, lithium, how many valence electrons does it have? 1. You know what? Let me back up for a sec. Maybe way back. Okay, so here's lithium. If we were to think of it in terms of electron configuration, all of these alkali metals have an S1. All of your alkaline earth metals have an S2. Here, we've got the S2 plus the P1, that gives us 3. The S2 plus the P2, so that's what we looked at and wrote down on our periodic table yesterday. So now we're using that information to think about valence electrons. Lithium and all of the alkali metals have 1 valence electron, so I'm going to put it right there. There it is. Strontium. And I need to keep going. I'm looking at the time here. So strontium has how many? 2. 1, 2. We have just filled up that S orbital. Calcium. It's also an alkaline earth metal, so it will be just the same. 1, 2. Oxygen. How many valence electrons? 6. So for oxygen, you have 2 in the S, and then the other 4 go into the P. Look at the order that they fill. 3, 4, 5, and 6. Then we get into neon. This is a good example to watch the order. So we know that neon, noble gas, happy, doesn't want to bond with anybody. How many electrons? Valence? 8. So the order would be 1, 2, 3, 4, 5, 6, 7, 8. Carbon, 4 valence electrons. 1, 2, 3, 4. Silicon, same thing. 1, 2, 3, 4. And our our transition metals, what did we say about those? How many? 2. And there's more to the story than that, but that's the story we're telling you right now anyway. Okay, so that's Lewis dots. Then we have some exceptions to our rule, and this is the last little bit. The key to this, and there's always going to be exceptions to all these rules that we talk about, but the key to this is knowing that when you do your orbital spin diagrams, that some elements, for the most part, are going to be more stable if they have either half-filled orbitals or completely filled orbitals. But if they're just kind of partially filled, 9 out of 10, something like that, it's not so stable. So half-filled or fully filled are going to be more stable. So when we go through these 3 examples, what we would expect from copper, you would expect copper to be argon, and then we go down to the 4s, so it's 4s, 2, 3d, and copper's all the way over to 9. So that's what you would expect. Everybody agree? Yep. Okay, so the actual, though, is that that's not really all that stable. If we could get that to be one of those orbitals to be half-filled or fully filled, it would be more stable. How easy would it be to get this to be fully filled? What could you do? One more electron. Where could it come from? The 4th energy level, that 4s. So if it comes from here and this goes up, now what we've got is a half-filled and a fully filled. So even though we would expect it to be like this, the actual configuration is 4s1, 3d10. So chromium, let's go to chromium real quick. So for chromium, it's in the same period as copper, so it's going to be argon 4s2, but it's 3d4 in this case. That's what we would expect. That's not the actual, because that's really not all that stable. So what should we do? It becomes argon, and then 4s1, 3d5. Because if you were to draw out your orbital spin diagrams, everything would be up, 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 up. I don't know if I said that right, but there's 5 ups anyway for that D block. And then, so you've got half filled for both of those. That's more stable than 4 out of 10. Okay, let me go back before we move on here. So it says that this means the electron configurations of all of the elements in the columns containing the elements copper and chromium do not fill as expected. So all of those are that way. Silver is just another example, very similar to copper. So let's turn this off and make it magically appear. So ta-da, there it is. Perfect.